So, hello and welcome to this second webinar of SDC Verifier series about our new product. Last time, a week ago, we have discussed how to build a model within the interface of SDC Verifier. We built a simple model. Today we are going to continue working with this simple model, and we are going to apply the loads, apply the boundary conditions, and I'll show a couple of tips how to work with the interface still. We are going to run the solution with Simcenter Nastran and maybe make a quick preview of the results. So what we are going to start with, we are going to go to the model itself. So I'm opening the model that we were building last week, and we're going to proceed with that. Meanwhile, I'll do a very brief introduction. My name is Lehishchuk. I'm in charge of operations here at SDC Verifier, and I'm joined today by my colleagues Petronek, who's leading our marketing and will make sure that everything goes smoothly, and will be managing your questions in Q&A box, and also Bohdan Melnik, who is leading our development, and in case of complex technical questions, he's always here to help. So don't hesitate to send your messages into the chat box or into the Q&A, and in the end of this session you will have a possibility to unmute your microphones and discuss. So last week we have built this model of a simple tower with kind of a deck on top. And I promised to show you a couple of things, but we haven't had enough time. So first of all, I think this design is not okay. And this these beams here are way too, it's good for a stiffener, but not good enough to support this deck on top. So what we are going to do first, we are going to replace some properties. So to do that, I'm going to go to Mesh, Update Element, and we'll do line element update elements property ID. I want to update property ID. So I'm selecting this, and in the list of in the methods of selections, I'm going to pick on property. And I will pick everything what is of this property, this yellow stiffener property, property number 7, this bar. And I will update it to I-beam that we had before, I-beam 200. Press OK. And everything we have here, I just double clicked on the screen to refresh. Everything we have here is now remeshed into an I-beam that we have below. It's way better, but it looks like our I-beam is intersecting the deck, and in reality, I suppose it should be supporting this deck. So I also wanted to show you how to make an offset, and with the same functionality of modify, update elements property ID, modify, update elements, and line element orientation, I am able to go to this elements. With a method, I will again select property is not okay, because now we will have this one. So I'm going to update them by on a line. So I'm going to go to update elements and select line elements offset, and I'm going to select on curve. Now from here, I'm going to pick all the curves that I have here. There might be 2 of them. I'm not sure which one I am meshing, so I'll click and select all of those. Okay. Now when I have selected this property, I'm highlighting it, and I have all of those I-beams selected. What I'm going to do now, I'm clicking OK. I'm going to do an vector offset or a vector offset along the vector, and I know that the height of this bar of this I-beam is 200 millimeters. So I'm going to do 0.1 along vector, the height, and I need to define this vector, and it should be negative in z direction. So I'm going to do here -1, pressing OK, and double click to refresh. Here you can see everything is updated, and now we have defined the orientation update for this. But one beam is not selected. Probably I skipped the line, so I'll do the same. Right click, and here we have previous command. So I'm clicking the previous command, and I'm selecting method on curve, and I'm going to select this curve. Both of them, I'm not sure which one is meshed. I'm going to press OK, around vector, along vector 0.1, OK, and -1 here. OK, done. Now when we have everything updated, we are going to proceed with the analysis. But before that, very important feature is to check if everything is connected. As you can see, we had multiple lines and stuff like that. What we can do is to check the model for coincident nodes. I'm going to first maybe one more thing I wanted to show you is how to measure a distance. So on this panel, couple of buttons. Here we have everything in terms of view. Do we want to show it with thickness or without, and so on. So everything view related is in this, under this button. Everything related to the distance measurements, so we can select one node to measure from, second node to measure to, and we will get a distance of 6.7 meters here. And the last thing I wanted to indicate on this button is this menu where we can check for coincident nodes. So I'm selecting coincident nodes, and either with a box select with a shift picking up all the elements, or I'm selecting all the elements, defining the tolerance and pressing OK. And here you can see that 1.4 thousand nodes were selected, but 0 of them merged, which means everything is there is no coincident nodes and all the nodes are merged. So we can proceed with the analysis. And the last thing before we go to applying loads and boundary conditions is a meshing toolbox. That's something I wanted to demonstrate also during the previous session, but we haven't had enough time. So if I'm selecting this, clicking on this button, I'm getting the meshing toolbox, which helps us to control and adjust our mesh. So as we can see here, the mesh is quite rough, and I would like to refine it. And there is plenty of different functionalities. I believe it deserves a separate video. Maybe we will make a webinar purely on meshing toolbox. I will ask some of our engineers who are mastering this tool to showcase it. So we can do that, but simple functionality that we have here is, for example, upgrade of mesh sizing. So I can select curves size and define increase by one number of element on curve. And when I'm clicking on this select button, if I'm picking up, if I'm clicking on a curve, it is updating and remeshing the adding extra element on this. So I added 3 elements here. I can also add 3 on top. 1, 2. This one is probably meshed on a surface, so that that requires a different method. But as you can see here, when I am clicking on this line, I am increasing the amount of elements, and I can refine the mesh much more. I can also improve the mesh here, So this is one of the options, but it also has functionality. Well, I can do the same with decreasing. So decrease by 2, decrease by 2 here, do a bit of a decrease here to leave it as it was before. A bit rough, but maybe we'll play with mesh refinement is in a separate video. So this, I will close it now. This panel on top is very powerful to set how you're going to set a view for the model, to measure, to showcase what do you want or don't want to show. So once again, we can turn off the elements and put on the geometry and play with that. So all the view functionalities are here, and you can find a lot of useful functionality here. Now let's go to the topic of our today's session. So now when we have built the model, we are supposed to analyze it. So we are going to go with loads and constraints. I have some load here. Let's remove it at the moment. Yes. And when we were building the model from scratch, we have 0 loads and 0 boundary conditions. What I suggest is going to be starting from boundary conditions. So we need to constrain our model. To do so, we go to constraints and we execute the right click and clicking on add. And constraints can be either nodal or on point, on a line, on a surface. I am going to select nodal constraints, and now I have a standard entity selection window where I need to pick the nodes which are going to be constrained. For this type of model, it's usually the bottom that has to be constrained. I picked 4 of them, clicking OK. Here we have to define, to set the title for the constraint set itself. So we are going to call it pinned. We can define a color, layer, and the coordinate system, in which coordinate system is important. In this simple model, we are working within one coordinate system always, within global rectangular. And then we can build either constraints by ticking the boxes with degree of freedom. So block everything to make it fixed, as well as you can undo this. Or you can click on these buttons. So fixed, everything is fixed. Pinned, it's only translations fixed. Free is nothing, no rotation. So rotations are blocked. For this model, obviously, not to make it over constrained, the best would be to make it pinned. Also, it is if you're building like portions of your model with a symmetry, you can use this symmetry constraints. It's sometimes confusing how to define it, so there is a nice handy buttons to define the symmetry constraints. But for our model, it's obviously pinned constraints in this corner. I'm defining this and pressing OK. And automatically the new window appears if you want to add something else, but we don't need that. And if the constraint button is, view constraints button is on, so you can see this text of this degree of freedom that you have blocked here. So you can turn it on and off. Let's keep it on to see what we have defined. And in our constraint, we have defined a definition of pinned, but the set itself is unnamed. So I go to this constraint set, select rename, and I'm also going to call it pinned. It is useful if you have multiple constraints, you can rename the set into the condition that you have, and then a definition could be named after the location or so. So you can say bottom legs pinned. And then in one pinned constraint, if you have other constraint definitions, you might want to add here extra conditions. So now when our model is constrained, we can proceed with the loads. And we're going to apply a couple of different loads today. So it is done through this FEMLoads section. And what we are going to do is to execute the right click on FEMLoads, select add, and select what we're going to start is simple. So yeah, there is multiple different ways. First of all, on mesh on geometry, how would you want to apply? Yeah, first things first, we need to add gravity. But we have body loads, we have nodal, elemental on geometry, and then we have SDC Verifier specific loading like wind load, buoyancy load for vessels, tank load, waves, applying multi-force in different nodes and on different selections. Let's start with simple. We need to have gravity in our system, right? So we select body load. And again, here the window is quite simple. What we have to do here is to do acceleration. It's even called acceleration / gravity. We make it active, and we do vertical axis is Z. So we are going to apply standard Earth gravity, which is 9.81 meter per square second. Negative in Z direction, so it's going to act in a minus Z direction. Nothing else, no rotational. So yeah, here you can also add translational accelerations, rotational acceleration, rotational velocity and stuff like this. But we are defining a simple gravity, pressing OK. And I need to, so it's, you will see that in definition it's 0, but you can add more definitions to this set. But in body loads, if you click on edit, it is our gravity load. Today we are going to work with load combinations. So we are going to apply every single influence on our model as a single separate FEM load. And I suggest and recommend doing this for everybody. So I just need to rename this and call it gravity. So now we already have a gravity load on our model, and let's add something else. Let's add another definition and let's make nodal. What we want to put here is, I would say, some kind of distributed weight or load over our structure. Let's say there's going to be equipment or people operating on top of this deck. So what we are going to do is here we have to select these nodes. I want to apply a force to each and every node, let's say along this line or even on this deck in general. So I will change the method into on surface, and I will select all of these surfaces of the top deck. Also, if you usually it is a pick normal. So one more important thing on how to pick the elements. If you execute a right click on the graphical interface, you have a possibility to either pick normal, pick query, or pick front. If I'm selecting front, the first thing which is in my view is going to be selected. I'm picking up this one, highlighting. So to all of these nodes, we are going to apply some vertical force now. I'm pressing OK. And here is the functionality of applying the loads. Much more options, as you can see, much more options than in accelerational load. So we can apply forces, we can apply moments, displacements, rotation, velocity, different accelerations again. Then we can apply temperature, pressures, lots of different stuff. We will keep our load simple, so we are going to select force. If we define components, we can apply force in 3 different directions. Or if we select vector, we can define this vector. Let's keep components. And again, we have Z as a vertical direction, and minus that is going to be some force applied. So I am going to apply, let's say, 500 newtons per each of these nodes. I hope it is going to be okay. You can also see that we are missing here one of the lines, wondering why. Maybe I have accidentally deleted it somewhere or so. Or when I was remeshing the surf, maybe it has disappeared. We will update this later, no problem. Or maybe we will keep it like this to see what's going to happen if we're missing these beams. Not a problem at all. So we are applying 500 newtons in this case. Again, our loads are limitless. So if you want to apply the loads in kilograms or in American units, you can do whatever you want. If I'm working in C system, I'm going to work with meters and newtons. So I'm doing minus 500 newtons in every of these nodes, and basically that's it. I have to define for this. I'm pressing OK, and the load has been created. As you can see, it's visualized here. It's pretty dense, but if you zoom in, you can see it's 500 newtons in each and every of these nodes. Maybe it's going to be too much, but we're going to preview the results later on. I can turn on and off this load toggle, so to see or not the load. Let's keep it, because if I activate the gravity, I will see it here in the accelerations. By activating, I mean just do a double click on this. If I define this one, which is untitled, let's rename it. Sorry, rename. Let's rename it into vertical force. Okay, we can do more. We can apply different loads. For example, we can apply side loads. We go back to fem loads, add. We can select either on surface or so, but let's do elemental in this case, for example, or let's keep the logic simple and do nodal again. So what I'm going to do is I'm going to apply add nodal load, but on surface, selecting method on surface. I'm going to select this surface, for example, just this one. I'm highlighting it now. So all the nodes of this side surface, let's assume there is some sort of impact or something. I'm pressing OK. And I'm going to apply a force in Y direction, let's say negative Y direction. So minus 300 newtons in that direction for each and every of these nodes. I'm pressing OK. That's everything I want to define here. And here is my side load of minus 300 newtons. All right, we have this one now. Again, going to give it a good name. Use good names for all of your projects. So side force, pressing OK. The load is applied, and maybe we'll go back to the File tab and save our model. So now when we have created three of pretty standard loads, let's do one of SDC Verifier advanced loads. And we go to fem loads again, add, and we want to apply wind on our model. It's I think it's nice for this case. I'm clicking on wind, and wind application load window appears. Certain things has to be defined here as well. First of all, do we want to know how many of these winds we are going to apply? We have X and Y direction. Let's say we will apply only one wind in X direction. So I'll call it wind X. But with this tool, yeah, I'll get to that. So first we need to define the vertical direction in our model. Obviously it's Z. And then the direction of wind itself, either in global coordinate system, or I click on custom and I can define a vector here. Excuse me. Now when I clicked on this vector, I have lost, here it is, cancel. So I'm going to select a global direction. It's going to be X, so wind X. Then if I don't need only one wind, but wind along a certain vector every a certain amount of degrees, I can select wind X, but then apply this rule every 30 degrees from 0, which is X, to 180. So 30, 60, 90, 120, 150, 180, or every 10 degrees or so, or every 45, up to you. But we want to keep this demonstration simple, so I'm going to apply only one wind load. You can define drag coefficients for your model for certain selections, properties or so. We keep drag coefficients from model, everything up to 1, and we can apply, we can pick a selection of a portion of the model to be subjected to wind. In reality, this tool does not take into account any shading or so. So if I'm going to apply a wind in X direction, it's going to blow from here toward along the X vector, which is which is going to definitely have some shading on this shells on top and also in here. But again, I'm keeping this analysis super simple. So I'm going to just select everything, and this wind pressure is going to be applied to all entities which are subjected to wind. Still, entities which are along X are not going to take any wind load. You'll see a nice visualization of this. Wind can be applied either by pressure or velocity. We're going to define pressure. Ground level is 0. If you remember, here we also have this dot. We started modeling with you from Z, from 0 in XYZ. So here is our ground level. You can adjust this ground level if necessary. And now we need to create this profile. And profile can either be loaded from the library. We have the library for different loads. I only have FEM, but we have other loads, I believe, in this in the library stored. What I'm going to do, I'm going to define my own pressure profile. It's going to have two conditions, and on the ground it's going to be 300 pascals, and on the height of, let's say, 30 meters, let's keep it similar. Well, let's do slightly different. Let's do 350 pascals. So there's the graph of wind pressure over height that you will see. So from 300 pascals on 0 to 350 on 30 meters over here. So it can be, you can apply as many conditions as you want, or load these pressures from a standard from library. When I press OK, wind load is being applied. Excuse me. If I turn on the load, let's see what's here. Edit.
Oleg, you need to turn on the loads on the top, I think.
Yes. Excuse me. And I'll turn off the geometry. Some weird things with mesh here, Bogdan. I've lost some of the mesh, maybe because I was remeshing here. But it's not a big deal for us at the moment. Just if I go to model, to properties. So is it a specific group selected now, Bogdan, or did I
You can try to show full model on the top near the machine toolbox. Yeah, there is
group. It's only one group. Show
yeah, just
active
click.
group.
Yeah, and then back to model. Back
to model here.
No, on the left from the selected group, you have the
show
button.
full model. Yeah, I see.
Yeah.
Okay, yeah, some visualization issues. Sorry for that. Thanks, Bogdan. So as you can see, our wind load has been applied over here. Has a distributed pressure which grows a bit over height, and as well to all the faces that are subjected to wind. It takes the portion and takes into account the angle and applies the distributed pressure of the wind load. So we have gravity, we have vertical force, side force, and wind in X direction applied to our model. Color with property colors. Also, all the property colors are now, I think, the same. Yeah. Okay, and thickness on, back to the view that we're used to. Okay, so we have applied loads and constraints to our model. We have 4 different loads and 1 constraint set. I think that's enough to go and run the analysis, which we call job in SDC Verifier. So now we've finished with our model section, and we go to the section of jobs. We have job 1. I'm going to click edit on this to create some analysis. So first of all, let's give it a good name. We call it static structural. And we have a certain settings here. First of all, we have some types of analysis, so linear, static, linear, buckling, or custom from imported results. We have analysis options. We have the results that we would like to request, so forces, stresses, displacements, and so on. If you want to also include strains or force equation, a constraint equation force, we can include it, but force balance is enough. Let's keep it as a standard. And we can define here a portion of model to be analyzed. So if in your model you have different groups or different selections, you can click on this edit button and play with these selections. In our case, it's very simple. We are going to analyze all entities under the loads that we have created. So the job was edited. I renamed it into static structural, and we need to create some loads and combinations for the analysis. First of all, individual loads. What is individual load in SDC Verifier? It is a combination of fem load and constraint that we have just created. So if I do a right click here and select add, I'm able to create here the loads for the analysis. What I can do here, either to create them by combining load and constraint, or have them from existing results. We don't have any results in the model before. So I'm creating by combining the fem loads. I'm selecting all of them with shift and pinned constraint. You can pick also to use constraint or not to do the inertia relief calculation, but yeah, since we have all of this created, let's use all of what we have just created. So we have fem loads and constraints combined. I'm clicking OK. And 4 individual loads are available in my analysis now. Next thing that I'm going to do is to do the combinations. We have a tool to create combinations from a standard immediately. So if I'm selecting this, this is a bit more extensive tool. And here you can define a specific combinations. So define the category to our loads and combine them according to Eurocode automatically. But we're going to do simple things today. So we just do standard load sets. I go to load sets, execute the right click and select create edit multiple. And how many combinations do we want to have today? Let's say 4. I'm selecting 4 loading sets, clicking on add. And we have 4 combinations included. What I want to have is gravity everywhere. We are calculating a structure on Earth, so gravity is supposed to be everywhere with no factor on it, multiplication factor. So factor 1 is okay, we press set. Then I want to include vertical force in one of it and a side force in the other. So we'll have a combination 1 is gravity plus vertical force, combination 2 is gravity with side force. And then I want to introduce wind to it. Maybe I'll put a factor of 1.1 on vertical force, 1.1 on side force, and 1, let's say 33 to each of those sets adding a wind. So I have selected all of this. I'm pressing OK. And now 4 combinations are created. You can add or modify later on. So I'm selecting create edit multiple, and it's possible to just add hundreds more combinations here or add the predefined combinations and so on. So what is load set? To those who are not familiar with SDC Verifier logic, load set is a linear combination of what is included in it. So if I'm having load set 1, where we have gravity and vertical force included, it's basically a sum of outputs of this to individual loads. The same we have for all of them. Also, we have a load group, which is envelope, which is overall maximum, minimum on, or maximum or minimum on a group. So we have envelope group of individual loads. So worst results of individual loads here. I see, Bogdan, one small comment for you. The logo here and logo here is slightly different. Need to adjust that. Okay. And we have envelope on load groups, the same. All of the load groups we have, so worst result on a load group is in here. So now when we have set up the settings for our analysis and we have set up the loads and combinations, we can finally run the analysis. So this can be done in a couple of ways. The most common one, I would say, is to go to the Home tab, where we have a big green play button, where we can analyze either the active job or by selecting rules. If you would have multiple jobs here, you would be able to select the jobs from list. The other way to analyze the job is to right-click on our analysis on our job and click Analyze from over here. So let's do the first one. So analyze, just clicking on this play button. SDC Verifier models. Okay, we need to update the model. No. So before running the analysis, it's good to update the model. I'm clicking on this update. We don't have any results, but so this window doesn't matter. I'm pressing OK, and the model has been updated, as you can see here at the bottom. I'm clicking on Analyze, and SDC Verifier runs the Simcenter Nastran. As you can see here, we are running the static structural job. Yeah, I think for those who are here, there is no need to introduce the Nastran solver. It is well known and it is yeah, common solver for many years. And as you can see, the calculation is done in like half a second. Obviously, it is a super simple model, but analysis is quick and convenient, and in 5 seconds of total solution time, the half a second of analysis itself, we have calculated our model. From here, we can call for a log file to see what was happening and how it was calculated. So standard Nastran log files, solver graph of a solver, but basically that's it. After the analysis is done, and we can see here that the output sets are created. After this, we can close it. And to prove that results are linked, or to check that results are linked, we can also go to individual loads, always select any of those loads. And if I click on edit of this, I will see the output set is linked to the load. So it means that the analysis has been done and the model has some results. After we've done this, the next steps would be previewing the results, doing the checks according to rules and regulations, and building a report. These are the topics of our next sessions. The only thing we are going to do today is to preview one plot to see what's actually happening with our model and maybe see if the loads need adjustment or so, because I'm creating the simple model together with you. Let's see if the results are realistic and good for the checks. So if we would go to, let's say, load group and envelope on load sets, let's see our maximum stresses here. So how do we preview results in SDC Verifier? We select individual load sets or load group where we want to check the results, do the right click and select a plot or table. Let's say first we do the plot. I'm selecting criteria plot. So we need to give it a name. Well, you will have a standard name if you skip this, so let's skip it, doesn't matter. We select the load on which we want to present the result. We select the category, it's going to be stresses, absolute equivalent stress with a default view I will show you views in a second, and on all entities. So basically nothing to adjust, stress on all entities. If you want to see other outputs, it is still possible: stresses, displacements, line element forces, and so on. For now, we are going to look on the simple stresses. I'm pressing OK to create this plot. It's added into the plot list in the bottom and also under the section of the load. We have plots, but first views. View in SDC Verifier is the way we are looking at our model. We will play with the view in our next session, but now I want to show this default one. We will edit this, and we see how the model is located for the plot. We have this nice and convenient get button, which takes the one from your active graphical interface position. If I'm clicking on get, it is reading the position. And here we have some settings, like do we want to show the legend, what would be the colors of the legend, and so on. There is one specific setting. I don't like magenta color in the legend, so I would go to advanced setting and select no magenta. Okay. Everything else with limits and stuff is going to be fine. We are going to have an automatic legend from 0 to maximum that we have. That's it. Pressing OK. And last thing to show today is to preview this plot. Right click on it and clicking preview. And SDC Verifier is plotting a result. Okay, we see we have some significant stresses in the corners here of 2000 megapascals. We will need to play with this model probably, because removing this stiffeners here is not the best. If I would go for a standard, let's say only vertical force, probably vertical force is causing this. I could do the same thing. I could do criteria plot of stresses, okay, and preview this plot. Yes, so this is coming from vertical force because we do not have this support here, I believe. For the next session, I will update the loads to make it look realistic and to show the results nicely. If we take a look on the gravity, criteria plot, gravity stresses, okay, and preview this gravity stresses, should be much more, still pretty heavy, 2.8. Is that correct? Equivalent, let's see, individual, no, load 1, gravity stress, preview, to 282 megapascals of stress in this corners, still a lot. So yeah, I haven't defined any specific loads to make it look realistic, just to show you how is that working. In our next session, I will prepare the loads that we have a nice realistic results compared to our yield and tensile strengths, and we are going to do checks on this model. 45 minutes exactly, that's the allocated amount of time that I planned for this webinar. So I thank you for your attention today.